The last, actually, one more type of graph in general is the histogram. We've talked about it a little bit, but I want to make sure we know how to set it up and use our calculator to make it, because it saves us a lot of time. And then the histogram, we can actually do a couple of more types of graphs within it just because they all kind of look the same, but they're technically different graphs. So a few rules about histograms. We talked about last time in last section about how histograms and bar graphs are pretty similar, except remember bar graphs were for categorical data and histograms are for quantitative data. So we're working with a bunch of numbers, not categorical stuff. So your bars have to touch each other this time because in a bar graph, the bars don't touch. In a histogram, the bars touch. So that's rule number 3. Number 1 is the same rule as with bar graphs. Each of the bars have to be equal in width, so you can't just make one wider than the other. And then your x-axis, because we are dealing with numbers here, you can't label your x-axis as ranges. So you can't say like from 500 to 600, 600 to 700. I'll show you how you have to label it. And then obviously label your axes, just like we've been doing. So let's set this up. It's going to be on graph paper. So I've set up my axes here with the x-axis labeled as sodium content in milligrams, and our y-axis, because we're talking about like how many times does this occur on the y-axis, it's going to be the frequency. So frequency just means like counts. How many times did this occur? So we're actually going to be making our histogram using our graphing calculator, and then we'll just sketch it out on paper because that's what you're going to be doing on the AP test as well. Any graphs that you make that you can on the graphing calculator, you're going to do that because it's going to save you a bunch of time. So let me pull up my graphing calculator here. And we've already gotten our data typed in, so I don't have to do that again. It's in order. It doesn't have to be in order. So that's one nice thing about your graphing calculator making anything for you. The putting stuff in order is just to make it easier for us to make certain graphs, like the dot plot and the stem plot. Your calculator can't do that on its own. So we did that. So to make that easier, we put the numbers in order. But when you're making a histogram, the numbers don't have to be in order. You can, but that's just extra steps. Your calculator can figure it out. It's fine. It's smarter than that. So what we're going to do to make this graph is to go into, at the top here, there's like the y equals button, and that's usually where, like, if you were to use this for any other class, you would type in your equation to have your calculator graph it. Well, we want like a statistics type of graph, so above it, it says stat plot, so it's going to be second, and then that button, the y equals thing, to get stat plot. So we can make like a bunch of graphs at the same time. That's what all of this is. We only want one of them, so I'm going to choose number 1 and hit enter. We want it to turn on because right now off is highlighted. So I'm going to hit enter so that it highlights on. Then I'm going to scroll down. So this is all the different graphs that your calculator can make for you. So this first one is like a scatter plot. The second one is like a time plot. We don't really care about that. We want this one with the bars because it's a histogram. So make sure that's highlighted by hitting enter. And then it'll ask for your X list. So basically, like on your x-axis, what numbers do you want to use? So mine defaults to L1 because it's the first one. It's also where we typed all our data in, so you want it to say L1. If you typed all your data in like L3 or something, then you want this to say L3. Frequency, we never touch. It's just going to stay 1. So leave it at that. And then remember, in case you don't have L1 in there, to type L1, it's second and then the number 1. Second and then the number 1. Okay, so we have all our settings set. Then if we hit graph right now, depending on how new your calculator is or if you've ever started it before, this is its default like window setting for like what it'll display. So right now you see 0 graph. This is just the axes, which isn't helpful for us. So what we're going to do is kind of change the X and Y axis, the window settings of our graph so that it actually fits to what we want based on our data. So I'm going to hit the zoom button. It's right here in the middle, right underneath a graph. Zoom, and then we're going to go down to zoom stat. I think it's number 9. Zoom stat is the one we want because it's basically fitting our window to the stats that we have. If your calculator has different numbering than mine, just make sure you look for Zoom stat. Hit enter, and then it fits it for us. So now we have a histogram. So this is our graph. We would draw this out on our paper, but obviously we have to label our scales, our x-axis and our y-axis to label the axes themselves, like what numbers we start at and stuff. So because we had our calculator do this, we want to be able to like just label it really quickly. So next to the graph button, there's something called trace, and trace just helps us identify parts of our graph. So once I hit trace, this little blinking thing came up. On this blinking thing, it says that for this bar, the minimum is 570, the maximum is 630. So that's basically telling us all the numbers included in this bar are from 570 up until 630, but not including 630. So pay attention to this less than sign here. It's not less than or equal, it's just less than. So all the numbers less than 630, not including 630, are in this bar. And this occurred 3 times. So basically in our data set, we have 3 numbers that's less than 630. And then if we hit the right arrow, this will move us to the next bar, and it tells us it's going from 630. And this is where, like, if we did have 630 in our data set, it would be included in this bar up until 690, but not including 690. And there are 4 occurrences of that here. And we can scroll through the rest to see what each of the bars contain. So that means when I'm making my histogram and drawing it out, then I want to make sure I label each bar and the x-axis correctly. So I'm going to start with the first bar. And because we're not starting at 0, I'm going to do this little zigzag at the bottom. This just means it's called a break in our graph, telling people we're not starting at 0. That's all. And so now we can start at any number we want. So I'm going to start at our smallest one, which was 570. And then I'm just going to make the same width for all of my bars. I'll just do 3 boxes because why not? You can choose. But that next bar is going to start at 630. So I'm just going to label this here. And so it looks like each of my bars are going by 60. And that's how you want to label your x-axis based on whatever your calculator is splitting it at. And then it ends at 930. So then from here, we just want to draw the heights of each bar. So it looks like the first one, I think we said, was 3. Then we had 4. Then 3 again, 2, 3, 1. Okay, just wanted to make sure I did that correctly. And then we're just going to label our x or y-axis. So again, your actual increments themselves, you can go by whatever numbers you want as long as your graph actually matches those increments and you're not skipping any numbers. Okay, there's our histogram. Okay, the last graph I want to make with you guys today is still a histogram. It's just the relative frequency histogram. So it's actually going to look pretty much the same as a regular histogram, a frequency histogram. But relative frequency specifically stands for percents, so proportions. Sometimes it's easier to use percents instead of like our actual counts or the frequencies if we have too many. Like if we have a really large data set, it's easier to just show things as percents instead. So our x-axis is going to look exactly the same as our regular histogram. So I already set that up for you. And then on our y-axis, instead of frequency, it'll be relative frequency now. So that means the highest it'll go is 100%. We obviously don't have that because it's not like we have any bar that goes all the way up and containing 100% of the data. So to find each of the bars, are like the percents, you're taking the total amount of data points that you have, which for us was 16, and dividing each of the frequencies by it. So our first bar for the 570 to 630, we had a frequency of 3. So 3 divided by 16, get out my handy dandy calculator, gives us a percent of 18.75%. So when we draw this out, it doesn't have to be super accurate, but I'm just going to go, we'll go have each of these lines be 10%. So that means 18.75 is almost 20%. So I'm just going to draw a line right here. Okay, and then we would continue doing this for the rest of our bars. So the next one we had a frequency of 4. 4 divided by 16 is a fourth, so 25%, which would end up being right, oh gosh, right here, and then you would continue for the rest of your bars. 2 out of 16 is 12.5%. So again, it doesn't have to be super accurate as long as it's like somewhere close. We should be fine. So I finished off our graph. As you can see, the shape of it generally looks like the regular histogram. It's just our labels for our y-axis are different. That's it. That's the only difference. So that's why it's like basically the same graph. But with our graphs, now we've basically graphed out the distribution of our data set. So a lot of times the whole point of making this graph is so that we can kind of analyze our data. So we want to be able to describe our distributions. And the way we do that is by talking about 4 specific things within our data set. So anytime we describe a distribution, these are the 4 things that we want to describe. The easiest way for me to remember is SOX. It stands for shape, outliers, center, and spread. So anytime the instructions will like literally say, describe the distribution. So that's exactly when you should be using SOX. So when we talk about shape, you guys use these words already in your summer packet. So there are 5 different ways you can describe the shape. So you can say that the shape of a graph is symmetric, meaning it's the same on both sides or pretty close to the same on both sides. We still count that as symmetric. Skewed right, remember, is when the tail or the shorter side is on the right. So you're going to see a graph that kind of looks like this. Skewed left is the opposite, so the shorter side is going to be on the left. Oh man, I drew that poorly. Let me do this. So skewed right is like that. Skewed left is like that. Okay, and then bimodal, unimodal, I put that in the same category because they'll never be, it's always one or the other, never both. Unimodal, meaning there's like only one peak. Bimodal, meaning there's 2 peaks. And for bimodal, specifically when we say 2 peaks, there's usually a pretty large gap in the middle. So if you still have a bar in the middle that's like even just close to the other 2 on the sides, that doesn't count as bimodal. Uniform is when all the bars are pretty much the same height all the way across. So that's uniform. So those are your options to describe the shape. You can even say things like slightly skewed left, slightly skewed right, slightly bimodal, because sometimes it's not like real obvious that it's skewed left or skewed right. So if we use the word slightly, it's like a better descriptor. Okay, outliers is the next one that I want to talk about. So outliers is, hopefully you defined it as any numbers that's like either really big or really small from the rest of your data. And if you look at our graphs of either the dot plots, the stem plot, or the histogram, we don't actually have any outliers in this distribution because looking at our histogram, it's not like we have any gaps towards the end or the end or the beginning, because there's no gaps, and there's no number that's like particularly big compared to the rest of our data set, or even particularly small. So that's what you're looking for. So if you see anything like that, where it does seem like it's far away from the rest of your numbers, then you can say like this number, whatever it was, seems to be an outlier. And we'll talk about next class how to actually figure out if something is an outlier or not. Okay, so outliers. Then the next one is center. When we talk about center, we basically want to mention what is the mean or what is the median. So mean and median are both ways to measure the center of our data set, because mean is just an average. So like, what's your average number? A median is like the middle number of your entire data set. And these numbers change. Sometimes it's better to use one or the other when we're describing a data set. Because if you think about it, when you average out your data set to find the mean, you're adding all the numbers and dividing by how many there are. But let's say you had an outlier in there. If you have an outlier in your data set, when you add them all up, that number when you add them all up is going to be a lot bigger than you expect it to, or even a lot smaller than you expect it to be. So if there's an outlier, to find the median, the outlier wouldn't really like do anything to the median, because the middle number would still be in the middle, whether or not the number at the end was like really big as an outlier or not. So a median is what we call resistant, because it is resistant to outliers. Whether or not your data set has an outlier, the median will basically stay the same. But a mean does get affected by outliers, so it is non-resistant. Okay, so that means if you have outliers in your data set, it is better to use a median to describe the center. If you don't have outliers in your data set, then you should use a mean, because it doesn't matter, it won't get affected. So that's how you choose which one to use to describe your distribution when we're talking about center. The last thing is spread. So spread is like how spread out your data set is. For that, we would either use standard deviation or the IQR. The formula for standard deviation is calculated using the mean, which means if you're using the mean to describe your data set, you're going to use standard deviation to talk about spread. You always have to use the one that goes with whatever center you used. If you use median to talk about your center, then you're going to use the IQR. IQR is the interquartile range. The formula for it is just your Q3 minus Q1. And we'll talk about that a little bit more next class too. Okay, so then all of these things are easily calculated in our calculator, because it's a graphing calculator, it can do everything. So let me pull that back up. So I have my, turn it on first. I have my list of numbers already, stat, edit. Here's my list of numbers. I'm going to have my calculator calculate everything for me. So from here, I'm going to go back into my home screen. I just wanted to pull up the list so you can see it. Home screen, this is where I sorted it earlier. You don't need that anymore. We can clear it. Doesn't matter if you do or not. Our favorite button, stat. We're going to go over to the right so that calc is highlighted, because we're going to do some calculations. And we are looking at our variable, one variable stats, the choice number 1. One variable stats, I'm going to hit enter. Basically, it's going to take everything in my L1 and calculate a whole bunch of things for me. It actually does everything all at once, and it's so beautiful. So, list, L1, because that's where all my data was. Freq list, it's a frequency list. It doesn't matter, leave it blank. Go down so that calculate is highlighted and hit enter. Oh my gosh, what are all these things that pop up? So the first one says X with a line on top. X with a line on top specifically is the symbol we use for the mean. So let me just jot that down in our notes really quick. X, and we read it as X bar. X bar stands for a mean. Okay, so they told us the mean is 718.125. So think about it, like 718.125 milligrams of salt, probably a lot. Okay, then it has a whole bunch of other stuff which we don't actually really care about until you see the one that says SX. SX stands for standard deviation. So again, let me jot that down. Standard deviation. So standard deviation itself, here it says it's 102.32. But the actual definition, or like in like plain English, is basically the average distance each point is from the mean. So we're basically saying, since the mean was 718, each of our data points, if we measured the distance from that data point to 718 by like subtracting or whatever, that distance right there, if we average them all out, that's what gives us our standard deviation. So on average, this is how spread out it is. That's what standard deviation is. Okay, and so we have mean and standard deviation really quick. If you scroll down on your graphing calculator, because there's actually more stuff, it'll tell you what the smallest number is, so that's the min, Q1. So you should know Q1 is like the first quartile, it's the middle number from your smallest number up to your median. The median is 695, Q3 is 820, the max biggest number is 870. So if you needed to calculate your interquartile range, it would be Q3 minus Q1, 820 minus 635 gives us 185. So our interquartile range is 185. So we're basically saying there's a distance of 185 between Q1 and Q3. So between Q1 and Q3, we're basically saying, since we've split up our data set into like quarters, that's what a quartile is, the middle 50% of numbers is between 635 to 820, and there's 185 numbers in that range to make up for our 50% of our data set. So that's what an IQR is, the interquartile range. Okay, so one thing that I want to mention now that we've gone over SOCs is if we ever had a graph for, let's say, like a categorical data set, if you made a bar graph for whatever reason, in a bar graph, you still have all the bars, and so like shape-wise, you can still like look at the graph and it kind of makes a shape. However, the shape doesn't actually make sense in a categorical data set, because in a bar graph, it's not like your bars have any sort of order to them. Like if I were to ask you, like, what's your favorite color? And then I graphed it out in a bar graph, any of the colors, I could have switched any of the bars into any other position. So the shape itself makes no sense when you're talking about categorical data. So that's one thing I wanted to point out to people. Like, you can't find an average, a mean of anything in a categorical data set. So you can't describe the distribution with categorical data sets. It just doesn't make sense because there's no shape, there's no center, there's no spread. Outliers doesn't really make sense either, because it's not like you have one thing bigger than the other. How would colors be bigger than the other? So that's why. Okay, so I know there was a lot of information here. There's just one more graph that I want to look at that's basically one that we've done already. However, this actually compares two different data sets at the same time. And this last one that I want to talk about is called the back-to-back stem plot. So my example, I've got a set of data about males and a set of data about females and their heights. This was taken from a sample of 14-year-olds from the UK, and they were randomly selected. Their heights are in centimeters because, you know, metric system. Anyways, so here we want to be able to make a back-to-back stem plot. And so it kind of looks like just like the stem plot, except there's two sides to it, so that you compare both like males and the females at the same time. So same thing is I'm going to enter all my male data into my calculator under one list, and then my female data into another list. So as you can see here in my graphing calculator, I put all the male data in L1, all the female data in L2. That way it'll order each of my sets of data separately. So I'm going to quit out of my lists. Oops. And then I'm going to get back into sort A. So second stat, go over to ops, number 1. So I want to sort my list 1. So that'll be all my male data. That'll get sorted. Calculator says it's done. I'm going to do the same thing. So second stat, go over to ops and sort A for L2. And then done again. So now when I go back into my stat edit to get into my lists, now both sets of data are in order now. Okay, so here, when we make our back-to-back stem plot, we need to make sure that our stems match for both sets of data. So looking at both sets of data, the first couple numbers are 1 and 5. Because I can only use the last digit as my leaf, my stems will have to start at 15. So writing this on my back-to-back stem plot, I'm going to have a leaf of 15, and it looks like for the males, that was L1, the smallest number was 151, and then 154, and then 157, 159. So that means I'm going to have leaves of 1, 4, 7, and 9, because that's the last digit of each data point. So when we talk about males, since it's on the left side of our stem plot, the smallest one always goes towards the stem. So it'll be 1, 4, 7, 9, going out this way. Okay, and then for the females then, in the 150s, we have 2, 3, 7, and 8, and that goes the normal direction. So 2, 3, 7, 8. And then our next stem would be the 16s, because 160 something, and then we continue on that way. So I'm just going to really quick go through and do the rest of my back-to-back stem plot. Okay, so I've completed my back-to-back stem plot. As you can see, females seem to be shorter because a lot of their numbers are smaller compared to the males, which kind of makes sense physiologically. Females do tend to be shorter. And then in the key, it looks a little bit different now because we have the two different sides for the leaves. So we write it as, I just chose the smallest numbers for each data set. The 1 line 15 line 2 stands for 151 centimeters for the male and 151 centimeters for the female. Okay, so this is our last graph that we want to make. However, I want to make sure we know how to describe the distribution here using this graph, because when we're dealing with comparisons, it's a little bit different than just describing a distribution for just one variable or one set of data. When we're comparing, we're still using SOCs. However, we don't actually need to state actual numbers. Like when we talk about the center or the spread for the mean, median, standard deviation, IQR, we don't actually have to say actual numbers. When you're dealing with one data set, you do. You have to say like the center is here. The mean of this data set is whatever number. The median of this data set is whatever number. But when we're just comparing distributions, when we have two sets of data, it doesn't matter. When we say compare, you're really just looking to see which data set has a higher center, which data set has a higher spread. So those are just the things that you have to state. You can't, like, just stating that the median for males is this and the median for females is this does not count as a comparison. You actually have to say, like, which one is bigger. That's the most important part. Whether you actually list out the actual numbers are irrelevant. It's not necessary. So like for this data set, when we talk about SOCs, I'll start with the shape. So it looks like for the males, the shape is skewed to the right because you have fewer big numbers than there are of the smaller numbers. It's actually almost uniform except for that last bar. So for the males, it's skewed to the right. For females, it's not, I don't know, this one's awkward because you have a lot of 16s. So I would say if we were able to split this up into a split stem plot, then we would probably be able to see better, because right now we only have 2 bars, so it's not really easy to look at the shape right now. But I would say it's also, or it would be skewed towards the left, just by a little bit, because we have fewer of the really short people, and then mostly everyone's in like the 160 range. So when we're talking about shape, you just have to list out the shapes of each data set. Then for outliers, it doesn't look like anybody is particularly far from the rest of the data, so we would say there's no outliers here for either data set. For the center, we would probably use the mean for both data sets, but even if we use the mean, because there's no outliers, if we use the mean for males looks like it's bigger because in general you have bigger numbers in the male data set than for the females. So we would just say the mean is higher for the males, and that's all you'd have to say. And lastly, for the spread, the male data set is more spread out because our range is bigger. If you want to talk about standard deviation and calculate that, cool. But really, you don't have to calculate it because even just looking at it, you can tell the male numbers are way more spread out than the females. So the male standard deviation is greater than the female standard deviation. Done. That's all you have to say. So when we compare two different data sets, you want to use words like greater than, less than, and then the shapes you just have to list out. But those are our comparison words that you want to use. Okay. And that is our lesson. I know this one was a little bit longer, so I tried to split it up into two different sections, but hopefully you got everything. Thanks for watching.